Gotta love Linux drivers. Cool. And also, let's go check up on our runs. I think we should have only killed the ones that were running on this box by doing that. Okay, so here's Enduro. Enduro's going along. And we have Breakout, which is pretty well set, it looks like. What's wrong? Score. There we are. Lovely. Interested to know why this is kind of cool if this is... I ran this from the right branch, didn't I? I will double check on the code here, but if this is actually the result we're getting out of this, this is amazing. I think it probably is. Let me see. Oh, look at that. This isn't going to show me, right? But we will double check on that. I'm pretty sure I know why that works as well. I think we kind of just, yeah, I think we hit the jackpot with this. I think we have a very nice sweep algorithm. And let me see, score. Oh yeah, look at that, 48. This thing was doing pretty well. We even have a nice burrito front on it. Perfect. Howdy. So sweeps are going well. I don't want to get distracted though for a bit. I want to make sure I finish this stuff. Well, this isn't gonna work. I don't think there's any, I don't think this works. I'll double check this. Yeah, you can't normalize across the batch like this because advantage is supposed to be over time, so this isn't going to work. This is definitely not working here. So one-step return doesn't help. That was Grok 3. I haven't tried it for coding yet. I wouldn't be surprised. I don't really use these models much for like writing code. I use them for docs and for like research and math more. Hang on, what's this? Adaptive horizon policy gradient. Advantage is going to be the sum one over ht, okay, plus, okay, so it's an adaptive horizon difference, which is determined dynamically per state. Greater than epsilon. Okay, so that's interesting. That's very interesting. The problem here is I'm going to guess that these experiments suck. That's usually the problem. Perplexity. I don't know, pin and D or whatever. Perplexity seems cool. It's a cool company. The thing is, I think that they're serving lower quality models for the most part. They're not serving giant models, right? It's more for just for search. Okay, so this is proposed for a completely different reason. $3 billion. They don't really have good tasks on this, but like, maybe. Uncensored R1. I mean, that's cool. Hmm. So if this is a parameter, but this is like something at least. But then what do you train the value function to predict? Learned advantage estimation. Yeah, that's crazy freaking expensive. States. It's not trained to predict advantage though. It's trained to predict Monte Carlo return, right? Oh no, wait, 'cause it's the difference between. Hmm. So this is what I was looking at based on reward variance. You should basically be able, the idea here is you basically should just be able to fit these parameters to the reward distribution. Where's this paper? Sources? No, not this one. I don't know if this paper exists. There might be a way of doing this efficiently. No, it's not R&D. Yeah, this one. Not quite what we wanted. Go back to generalized advantage estimation. This thing is just so hard to get rid of. I see we have some folks on YouTube now, so what I'm currently doing is I'm seeing if there's any obvious way of replacing generalized advantage estimation in reinforcement learning. It's a really obnoxious requirement at the moment because essentially this thing makes it so that PPO will not work on multiple environments without retuning at least a couple of the hyperparameters. So if we could get rid of this thing with something that like either fits its own parameters or bypasses that requirement somehow, it would make PPO a lot more robust and require less tuning. Okay, so lambda equals 0. There are a couple things we need to do here. The thing is, we know that this is, with lambda equals 0, this thing doesn't work particularly well now, does it? Yeah, this is lambda equals 0. Yeah, based on the values of lambda that are common, it seems like you mostly want the lambda equals 1 formula. This just interpolates between the two. So you mostly want this one, but a little bit this one. The problem is this one has the discount factor on it. Pretty much any heuristic I can come up with, right? There's going to be a way to screw with. Like any heuristic I come up with based on the distribution of rewards or similar, I'm sure I could come up with something that would work for like all the arcade games where there's kind of just one source of reward. But I don't think it's going to be particularly robust. Hang on. So this only uses, you're only using the next two value functions here. How screwy would it be if you just lerped them instead? Hang on, does that even do anything for me? Well, you're training the value function to predict. Hang on. Let me look at something. Yeah, so you're training it to predict the discounted returns, right? What I'm currently thinking here, so you can't try to have this thing just predict like the sum of rewards from now into the future forever, right? You have to have it be discounted, because otherwise that thing explodes. So you want it to be discounted reasonably. But that's only because you're making a single prediction, right? What if instead of predicting discounted return, you were just to predict the reward several steps into the future, like at each step. Let's say that you predict the reward 32 steps into the future, right? All right, let me go through this with Grok. Do they do this? It's planning. I mean, this is kind of a crazy method that I just cooked up. It could do something though. It's just reward minus value, right? I wonder if anybody's tried this ever. I don't think so. Okay, hold on. This maybe? Let me see if I understand this. So it took my method. Well, hang on. This is not... I don't think you can train it to predict... No paper. This is me mucking around with generalized advantage estimation and bouncing stuff off an LLM. I'm trying to see if we can do something to replace the lambda and gamma parameters. Rewarded each future step. We could sum this. Okay, hang on, I think I got it. Likes to write so damn much. I think this does it. So you get your loss function like this, right? And then your advantage, you sum reward minus value, which is equal to sum reward minus sum value, right? That's equal to sum reward minus sum value. So it only matters that you get the magnitude of the reward right over the course of your predictions. That gives you a nice loss function. The value function is inaccurate. Yeah, it should be averaged. That's fine. Value functions early in is noisy early in training anyways. Okay. Well, we have the idea. We have the idea. I have no idea whether this works or not. See, it's 5. I could try to implement something on this at least. I could try to implement something. How are you going to predict words into the future? TD into the. I'm just going to change the size of the value head. Like the value head outputs one variable, right? What if I just make it output 32 variables? I mean, if you think about it, right, a lot of the point of doing generalized advantage estimation. Where did it go? If we look at the paper here, there's kind of some key insight. So generalized advantage estimation is a sort of an interpolation between these two formulas, right? Using lambda to interpolate. It's not just a lerp, but it is an interpolation-ish. This is the more important of the two formulas because lambda is almost always close to 1, right? Usually it's going to be like 0.9 at the lowest. So what this is this is just training the value function to predict discounted returns. But this is because you only have a value function for one step, right? This is assumed to be a single variable. So if I just predict the value function out at each step into the future, doesn't that just give me more information? And I don't need this gamma parameter anymore? I think it should. I mean, we can start implementing it a little bit, right? The problem with the TD methods, right, is having to have the tunable parameter. Same as G, same as everything else. So that means that you can't have the same algorithm work on a ton of different environments, like the same hyperparameters. TD error target is its own bootstrap. So it validates. How are you validating your value head without supervision? You do have supervision though, right? So I guess technically there are going to be some samples in your batch where you don't have predictions out that far. But you predict 32 time steps out into the future. You're going to collect a bunch of data, right? So you're going to collect a bunch of rollouts, and then you're going to be able to use segments, and you're going to be able to use the rewards that you actually got to supervise that value loss, which is the exact same thing that you do with generalized advantage estimation anyways. Okay, so you don't have advantages here, right? So the first thing value has to predict reward. Let me make sure I get the indexing correct on this real quick. I think you have to shift it by 1, don't you? I think you have to shift it by 1. Yeah, T next, okay. Values, T next, C rewards minus C values. Okay, so this is just directly the next reward, right? So I can actually leave this in place. Advantages plus values. Advantages plus values. Yeah, that ends up being the same. This is just one step prediction, so this is going to suck. Oh, if you're going to collect samples to update, that's okay. You can do regression. Exactly. Each environment will have its own distribution to learn. What do you mean each environment? Well, yes, you have to. Yeah, you have to run the learning algorithm on each environment. That's fine. The thing is the hyperparameter tuning, right? Like right now, you have to run 100 experiments, and the number of experiments you have to run depends strongly on the number of hyperparameters that you have to tune and their sensitivity. So if we can remove lambda and gamma, which are two of the most annoying ones, then that's going to put us in a pretty good spot. And then we'll basically just have to tune learning rate, and most of the other ones are just scaling params. I guess there's entropy as well, but we'll deal with that one separately. So obviously this isn't going to work. This is just a really bad baseline um, with the one-step rewards. Now, let's do 32. These values. Size 32. Do that. Sensitivity comes from each end having a separate distribution. How are you going to adjust your reward predictor without hyperparameters? Well, because it's predicting the reward at each step, right? It's not predicting returns. So at each step, your model is going to predict the reward at the next step, the reward at the second step, the third step, out to 32. Because right now what you do is you essentially predict like a soft, exponentially decayed sum over those. So instead of predicting an exponentially decayed sum, you're just going to predict each one of them individually. I think we need to do we don't need T next at all, do we? Okay. Reward can be very noisy. Well, it's already hard to predict in GAE, right? Like, these are problems with GAE as well. Be skewed. How it's going to work, agent ends the loop. So this is a learning time thing, right? So you collect your rollouts. It's on policy, okay? So you collect your rollouts. You're going to do PPO as normal, but instead of using JE, which is going to compute an exponentially decayed sum, and then it's going to compute a loss with that and the single value prediction, right? The value being trained to predict the exponentially decaying sum. Now, instead, you're training a value head that has 32 outputs to predict the reward at each of the next 32 steps. So the algorithm is almost the same. It's just that you're predicting 32 separate rewards instead of predicting an exponentially decayed sum. And the cool thing about this as well is, yes, the individual values are hard to predict, but you only have to get the sum right? You only have to get the sum over the next 32 steps approximately right, and that'll be what's used as the advantage. Now, maybe that thing needs to be decayed as well because your predictions into the future are less accurate or something, and then we'll have to think of something for that. But, initially it seems reasonable. Right, but all that it does is it gives you, like, what are those parameters doing, right? They're giving you an effective horizon to look at. All right, like if you have a 0.9 gamma, then your effective horizon is about 10. If it's 0.99, then it's about 100. Here, let me give you a very, very strong motivation for trying to find an alternative to JE. The ProcGen benchmark was introduced with the assumption that you're not supposed to tune the hyperparameters per environment, right? You just have one set of hyperparameters and you see what generalizes. And people came up with all sorts of fancy algorithms and none of them worked. Well, these guys solved all of ProcGen just by hyperparameter tuning per environment. And it turns out that the optimal gamma and lambda vary dramatically across the different environments. So it's probably impossible for any algorithm that relies heavily on that lambda and gamma to generalize across all these m's. So as long as you have any method that uses these types of parameters, you're kind of just screwed. That's the issue. Average reward papers. I mean, are there any that are decent? Like reward averaging and any sort of like post processing on that doesn't do the same thing. I mean, if you have references, by all means, let me know. Okay, I think this one is good, and then you do this. And then you also have to check to make sure. I think this might do it. So this gives us continuous setting. It's the same thing. There's no reason they should be different for discrete or continuous. The value head is completely independent of the action head, right? Or can be. YouTube's not going to let you post a link. If you put the paper name, they'll all grab it. Actually, we can just do this. Perfect, right? Yeah, post the paper name. Discounted is not an optimization problem. That's funny. All right. Sutton paper. What? Maximizing the average reward. All right. Thank you. Yeah, I'm a little suspicious of the framing of this, they're essentially saying that it biases, like having this discounted sum biases your optimization, so there's no longer a solution or something. But like, you can't say it's incompatible with high dimensional continuous control when this is successfully used on high dimensional continuous control all over the place. So, like disproof by counterexample of the thing actually working. But the thing is, like, do they actually have any alternative to this? I mean, this is their alternative. They just link a bunch of papers from the 90s with dynamic programming. That doesn't do jack for this. No, you're good. It's just like, this is like, this is your Sutton paper, where it's like, yes, theoretically, the thing that everyone is doing is not well grounded. Okay, what's your alternative? Links a bunch of papers from the 90s that are clearly not applicable here. No experiments paper. I mean, that's a Schmidt-Hoobering right there. And it's not even Schmidt-Hoober. Well, yeah, Sutton. Of course he's got lots of papers, right? Sutton is like godfather of RL, but the problem is this type of a thing, this is not particularly helpful, right? Like, look, literally, like, look at what this is, right? There are several dynamic programming algorithms for finding optimal average reward policies. Okay, nobody's doing tabular RL, so that's completely redundant. First RL algorithm to maximize undiscounted average reward. I don't think any of these works. Q-learning. This is before deep Q-learning. This is tabular. As you are not able to find it's an active. Well, that means it's an inactive research area, right? Quite the contrary. I think we're just going to do this. This gives us rewards. This gave us 2. I don't know so many papers about RL without gammas. Yeah, I mean, it's a pervasive issue. think I need to compute a mask here as well, don't I? Load rewards. Okay, so there's a little Python function. Fucks with this a little bit. Go ahead and drop the paper name. The target for the bias and advantage are calculated without discount factors. The average return is subtracted from the reward. Does that actually work? Okay, this looks like something. I'm gonna stick this in the rock. Time to Grind was dealing with undergrad. How does it get this wrong from the link? That's incredibly stupid. Apparently you can't paste links. I'll drop the PDF in next. It found it. You just have to give it the name of the paper. It has browsing, but it doesn't have link following. Policies are always denoted pi in RL, right? Yes, except when they're not. How the heck? There's no way that works, right? I'd be incredibly surprised if that works. I mean, I will play with this. I want to finish a little bit on this implementation because I gotta go soon. But I will be very surprised if that one works. Well, the thing is that, like, I assume that by default in RL, here's the tough thing. I assume that the experiments of any given paper, even if it's like a NeurIPS oral, I assume the experiments are wrong. Because that's usually the experiments are wrong. Like, more often than not, I think that the majority of papers are just wrong. That's the annoying thing. Yep. Well, this is the whole idea with Puffer. I don't know how much you've seen my other work, but like, why is the majority of RL research wrong, right? They don't run enough experiments, and they don't run full hyperparameter sweeps on their method, and they write terrible code that's like irreproducible, right? So we have very simple and clean code, and we have all these environments that run at 1,000,000 steps per second. So now you can run thousands of experiments on your one GPU that you can afford on your academic budget. And you can do everything from breakout at 1,000,000 steps per second, which is not that hard to make, all the way up to neural MMO at 1,000,000 steps per second, which is like one of the most complex RL environments out there, with hundreds of agents and a dynamic economy and all sorts of stuff. And this library is growing constantly. Compute advantage as well from this, right? Do you need this? Hang on. You don't need this, do you? Oh, you need it for, okay, so we do, you do need this, hang on. Started a long time ago. Thank you very much. I mean, I just stream all my work, so I'm kind of always doing this stuff. The thing I'm really excited about, I don't know if you've seen the hyperparameter sweep stuff, but yeah, I think the hyperparameter sweep stuff is really promising. We've got like, yeah, we're like automating. We're really, really automating the process of hyperparameter search. Building stuff properly. Yeah. Well, it drives me nuts because nobody's done it. Like, you look at all these RL repositories, and it's like the most insane code you've ever seen. I say as I write this god awful transpose. So advantage should still be good. This is the same. Nah, you can train Pong with that just fine. I see. That's obnoxious. Keep getting baited. Thought I would have to get 20k of compute. Oof. Well, to be fair, without PufferLib, you would be kind of screwed. Everything else is about 100 times slower, so. We like Puffer. Puffer is very fast. Oops, it's not done, it's rewards MP. B reward block, B mask block, right? How'd that happen then? That's fine, actually. Hold on. So Misk says that my Python is slow. No big deal. I can fix that. The heck? Well, I mean, that is doing something. Isn't there should be a group here, right? Yeah. It's only slow because of my Python code being unoptimized. We can easily optimize that. I mean, that's kind of crazy though to just like this is literally the first time I'm running it and it does something. That's pretty cool. Well, I'm gonna let this run. I'm gonna go get dinner, and then I will probably no. This is breakout. I will probably be back after dinner because this is kind of exciting. I might just want to keep working on this tonight. We'll see. We'll see how I feel after dinner. But yeah, thanks folks for tuning in for now. I'll be back with more RL dev soon. And if you're interested in following any of this work, it's all open source. Just go to puffer.ai. You can check out all the code. Please star it. It really helps when people star the repo. You can also join the Discord to get involved, or follow me on X for more reinforcement learning content, as well as notifications of when I'm live. So yeah, thank you, and hopefully we have something here. This was kind of just a one-off. We'll see. I might keep working on this.